Now, talking about the helium atom, we're switching on the perturbing Hamiltonian, which is the interaction between the two electrons. So we're trying to find the first order correction to the changes in energy eigenvalues, so be this for the nth eigenvalue. So we've seen this before. This is the formula from perturbation theory for your nth eigenfunction. Okay, here's your perturbing Hamiltonian H bar. Now these wave functions here now are anti-symmetric wave functions. Okay, so it's a bit of a shorthand here. Well, I don't know if you can see it, the line above, but these here will be of the form U1, U2, blah blah blah. All right, this is a bit of a shorthand here. Now it works out. Again, this is sort of, well, you can try. It's thrown at you, but when n is 1, it works out, so you'll be a 1, 1 here, so you'll have h dash 1, 1. It works out that this is the difference between two integrals. Now you can try playing with that yourself to see if you can, how far you can get in deriving it. Because this is more grade level, I guess, but just to give you a taste of what's coming. So it works out that this first order correction to the energy eigenvalue is the difference between two integrals, this and this. And for the second order, well, the first order, but second wave function, the next excited level of energy, if you like, is the sum of these two, the same two integrals. And you may ask, well, where the hell does that come from? Good question. So, yeah, not explained in the text. You could try deriving it if you like. For example, these, like this term here, the perturbing Hamiltonian, H dashed, does not involve operators on the spin, has no effect on the spin. So you'll notice these integrals here, there's no mention of spin, right? They're all spatial. They're all about spatial variables, R's, various R's. Okay. So that's just given to you. That's a ICBST, and well, I mean, you can try, play around and see how far you can get. Okay, now interpreting these two integrals, one is the I1. This one is fairly intuitive in the sense it's familiar, similar to classical mechanical type reasoning, and the second one is totally alien. That's a purely quantum mechanical phenomenon, has nothing to do with quantum mechanics. So for the first one, if you have a look, you've got U1R1 starred, U1R1. So multiply these two together and you've got yourself a probability density, right? It's like a probability density for particle R1. And a similar logic for these two, U2 star R2, U2 R2. So you multiply those two together and you'll get the modulus of U2 squared. That's from Born's interpretation. That's a probability density for particle 2. So you've got rho R1, rho R2 divided by this. Okay? So so these are, in a sense, charge densities for the two particles divided by their separation, R1, 2. So that intuitively makes sense using classical mechanical reasoning. That seems plausible. Right? So it's saying here, it's like a Coulomb energy due to this for two classical interpenetrating clouds of charge. Okay? So you've got this sort of charge density road here. Okay. Now for I2, this one here has no classical analog. It's labelled the exchange energy, and there's no intuitive, familiar, classical interpretation. It just comes out of the mathematics. All right. Okay. Now, evaluating these two integrals, in other words, to find the energy correction, first order, is complicated, not given, but textbook claims fairly straightforward. Now, the interesting thing is that these two integrals end up both being positive. Okay, they're both positive numbers, and given this formula and this formula, if these I1, I2 are both positive, you can just see immediately from this formula and this formula that E2, first order correction, must be larger than E1, because here you're subtracting something positive, and here you're adding something positive, and that's positive, right? So just obvious that this one here must be larger than that one. Okay? So how do you interpret that? Well, so what does that mean? So E1 is the lower energy, but yeah, pretty well by definition, as the one here is like your first, your eigenfunction 1, eigenfunction 2. So this is more excited than that one. Okay, so so what does that imply? So when the spins are parallel, in which case, like these first three cases, yeah. So when the spins are parallel, the particles keep their distance. Does that make sense? That means these are further apart. Hold on, I'm just trying to think through the logic. So E2 is greater than E1. That just came out of the math of the plus and minus here. So if they're keeping their distance, this distance here is larger, so 1 over larger is smaller, and that would be consistent with the Pauli exclusion principle. So when you have the spins in the same state, the two particles can't get close. They're not allowed to be close together. That's excluded from the Pauli exclusion principle. Right? So those results the fact that you get this kind of thing is consistent with the Pauli exclusion principle, right? And furthermore, we're talking ground state helium. So in the ground state, without the perturbation, hydrogen ground state energy level, that corresponds to an eigenstate that's spherically symmetric. Okay. This sort of form, a hydrogen wave function of psi 1 naught naught. So n is 1, L is 0, and m is 0. Okay. So now you're talking 2 electrons because it's the helium atom, right? So they have the same U, the same wave function U. So if that's the case for the ground state helium energies, so this is equal to that, and similarly for all three of them, the first three cases. So these are all 0. So in other words, for the ground state energy of the helium atom, without the perturbing Coulomb potential, without the H dashed, then the ground state energy ground state wave functions are 0, right? So the triplet, 1, 2, 3, the first three, they're all 0. So that means that the ground state energy of the helium atom without the H dashed is the singlet. It has to be the singlet. It has to be the fourth